Hello friends, here in this video we are going to see the comparison of the three cycles, that is Otto cycle, diesel cycle and dual cycle. Let us get started. Comparison of Otto cycle, diesel cycle and dual cycle. Here, while comparing, I'll assume two things, that is which will be common for these three cycles, and that is the comparison is based on for same compression ratio and heat supplied. So here my assumption is that the compression ratio is same for all three cycles and even the heat supplied is same. Now before going on to the comparison part, the first thing we should do is draw the PV and TS diagram of all three cycles superimposing on one another. It means here I am going to draw these three cycles on a single graph. Let us get started. First will be the PV diagram. So here I am going to draw the PV and TS diagram for all three cycles. Now the first cycle is Otto cycle, so I'll draw the diagram for Otto cycle. Now this is the first process from 1 to 2, called as isentropic compression, or it is also called as reversible adiabatic compression. Next, process 2 to 3 in case of Otto cycle, because first I am drawing Otto cycle. Process 2 to 3 is constant volume heat addition. So keeping the volume constant, the heat is being added from point 2 to point 3. Next, after this, process 3 to 4 will be isentropic expansion. So process 3 to 4 is isentropic expansion. Like 1 to 2 was isentropic compression, 3 to 4 is isentropic expansion. Next, process 4 to 1 is constant volume heat rejection. So here I can say that during process 1 to 4 the volume is constant. So V1 is equal to V4, and during process 2 to 3 again the volume is constant, so V2 is equal to V3. Now this is the Otto cycle. Next, diesel cycle. Diesel cycle also I will draw it onto the same diagram, and here the condition is for same compression ratio. Compression ratio is nothing but V1 by V2. It means that compression for Otto cycle and diesel cycle will follow the same curve, which is from 1 to 2. So while drawing the diesel cycle, 1 to 2 is the same process as it was there for Otto cycle, isentropic compression. Next, process 2 to 3. In case of diesel cycle, it is constant volume pressure heat addition. So here the pressure of point 2 and 3, they are same, P2 is equal to P3. Constant pressure heat addition. Next, after that, process 3 to 4 is isentropic expansion, like it was there in Otto cycle. The similar expansion process will be there for diesel cycle as well. Now here I'll give this as this point 3, I'll denote it as 3 dash, and next here point number 4, I'll denote it as 4 dash. So 3 dash to 4 dash indicates the expansion process for Otto cycle. Next, after that there is heat rejection. The expansion process, this was for diesel cycle, or for Otto cycle it was from 3 to 4, and for diesel cycle it is from 3 dash to 4 dash. Next, here after the expansion we have heat rejection. Even in case of diesel cycle, the heat is rejected at constant volume, so it will be rejected from 4 dash up to point number 1. So here we can say that from 4 to 1 the heat will be rejected for diesel cycle, and even here I can say that V1 is equal to V4 is equal to V4 dash. Now after drawing the diesel cycle, that is superimposing it on Otto cycle, next I'll draw dual cycle on this PV diagram. Now in case of dual cycle, here the condition is for same compression ratio, so compression will follow the same curve, which is from 1 to 2, that is the isentropic compression. Next, process 2 to 3, it will be constant volume heat addition, keeping the volume constant. In case of dual cycle, I'll give this point as 3 double dash, so the volume is constant from 2 to 3, constant volume heat addition. Next, in case of dual cycle, the heat is added at constant volume as well as constant pressure. So after constant volume heat addition from 2 to 3 double dash, there will be constant pressure heat addition. From 3 double dash to 4 double dash. So here I'll say the pressure is constant. P3 dash या तो P3 double dash is equal to P4 double dash. Next, here after the heat addition process from 3 double dash to 4 double dash, there will be expansion from 4 double dash. Expansion is reversible adiabatic or isentropic for dual cycle, and this will be from 4 double dash up to point number 5. So here from 4 double dash to 5 we are getting the isentropic expansion. Next, from point number 5 up to point number 1, it will be constant volume heat rejection. So V1 is equal to V4 is equal to V4 dash, and that is equal to V5. It means in all 3 cycles the heat is rejected at constant volume. Here on PV diagram I have shown all 3 cycles, that is Otto cycle, diesel cycle and dual cycle. Now here after drawing the PV diagram, next I'll show these cycles on TS diagram as well. So starting with Otto cycle, the first process is isentropic compression. So it will be shown on TS diagram with the help of a vertical line. So from 1 to 2, we have isentropic compression. It means entropy remains constant, that is S1 is equal to S2. Next, after isentropic compression, we have constant volume heat addition for Otto cycle. So here I am going to draw a constant volume line. This line here I am writing V is equal to C, that is the volume will be constant on this line. So the heat addition takes place at constant volume. It means after point 2 the heat will be added on this line up to point number 3. So this is the constant volume heat addition, and as we see here, during the heat addition process temperature rises from point T2 up to point T3. Next, after that from 3 to 4 we have isentropic expansion, and it will be shown on TS diagram with the help of a vertical line like it was for compression. So 3 to 4, that is isentropic expansion, and here the entropy S3 is equal to entropy S4 because it is constant entropy process. Next, from 4 to 1 it is constant volume heat rejection. So again I'll draw a constant volume line. So volume V is equal to constant, and then there is heat rejection at constant volume. So from 4 to 1 the volume would be constant. Now this is the Otto cycle on TS diagram. Then over this I will draw diesel cycle as well. In diesel cycle, here it is mentioned that for same compression ratio, it means the compression ratio from 1 to 2, the process would be same for Otto cycle, for diesel, and even for dual cycle. So 1 to 2 will remain constant, isentropic compression. Next, the process 2 to 3 for diesel cycle, it is constant pressure heat addition. So here, as I have drawn a constant volume line, now I will draw a constant pressure line. And this constant pressure line P is equal to C, it will be less inclined compared to the constant volume line, that we have to remember. And here process 2 to 3 is constant pressure heat addition. So I'll go on adding heat over this constant pressure line. From point 2 up to 3 dash. This is the constant pressure heat addition. Next process is isentropic expansion. So it will be shown with the help of a vertical line, keeping the entropy constant. So from 3 dash to 4 dash, it is the isentropic expansion for diesel cycle. So here S3 dash is equal to S4 dash. Then from 4 dash up to 1, it will be, as we see here, 4 dash to 1 constant volume heat rejection. So the heat will be rejected from 4 to 1, or here if we say 4 dash to 1, that is the constant volume heat rejection for diesel cycle. So here I have drawn Otto and diesel cycle on TS diagram. Next is dual cycle, and again we have to keep the compression ratio constant. So process 1 to 2 will be same for dual cycle as well, but if we see in case of dual cycle, the heat is added first of all from 2 to 3 dash at constant volume, next from 3 double dash to 4 double dash at constant pressure. So there are two heat addition processes. So first, from point number 2, the heat will be added at constant volume. That is, I'll write down here, the point is 3 double dash. And next I need to draw again a constant pressure line, because from 3 double dash to 4 double dash it is constant pressure heat addition. So like here I have drawn a constant pressure line. Similarly, parallel to this, I'll draw another constant pressure line, but I have to see here that this constant pressure line should be less inclined than the constant volume line. Now the heat will be added over this line, keeping the pressure constant, that is from 3 double dash to 4 double dash. The pressure is kept constant, and from 2 to 3 double dash it was at constant volume. So there is constant volume heat addition first, next there is constant pressure heat addition, after that there is isentropic expansion from 4 double dash to 5, so the entropy will remain constant. From 4 double dash to 5, the entropy will remain constant. So here S4 dash is equal to S5. I'll write down S4 double dash is equal to S5, entropy remains constant. Next, from point 5 to 1, as we see here 5 to 1, it will be constant volume heat rejection for dual cycle, constant volume heat rejection. So here I have drawn the 3 cycles on TS diagram as well. In this I'll write down the notations which I have used here, that is 1, 2, 3 and 4, it represents Otto cycle. So from 1, 2, 3 and 4, similarly 1, 2, 3 and 4, it represents Otto cycle. Next 1, 2, 3 dash, 4 dash and 1, it represents diesel cycle. 1, 2, 3 dash, 4 dash, it represents diesel cycle. And at last 1, 2, 3 double dash, 4 double dash, 5 and 1, that represents the dual cycle. So first of all, as I have written here, the last cycle will be dual cycle. I'll write down it here, that is from 1, 2, 3 double dash, 4 double dash, from that 5. This complete cycle, it represents dual cycle on PV and TS diagram. Here, as I have drawn the PV and TS diagram of 3 cycles superimposed on one another, and I have even given their notations. Now, when I'm comparing, I'll compare the efficiencies of the cycle, that since the efficiency of air standard cycles, that is the thermal efficiency, is given by. Now the general formula for thermal efficiency of air standard cycles, see Otto, diesel, dual, these are considered as air standard cycles because they use air as the working medium, and here we are neglecting the amount of fuel because compared to air the fuel quantity is quite less, so we are calling these cycles as air standard cycles. And for that the thermal efficiency formula is given as, I'll write down, the thermal efficiency is equal to work done upon heat supplied. Now, therefore, thermal efficiency is equal to work done is nothing but from the heat supplied, that is QA is the amount of heat added or heat supplied, QR is the amount of heat rejected. So from the amount of heat added, if we subtract the amount of heat rejected, we are going to get the amount of work done and divided by heat supplied, which is Q suffix A. Now here I can write this as QA upon QA, that will give me 1 minus QR upon QA So here from this we can say that, as here I have assumed the parameters in such a way that for same compression ratio is same and even the heat supplied is same, so QA value will remain same for all the cycles. It means QA, that is the amount of heat supplied, can be treated as a constant value. So here I'll write down, since the amount of heat supplied for all the cycles are considered as same. That is, here I am considering the amount of heat supplied for all the cycles as same. So if QA value is same, 1 is a constant value, the only parameter on which the thermal efficiency of the cycles depends is QR, that is the amount of heat rejected. So therefore the only parameter on which the thermal efficiency depends is heat rejected, that is Q suffix R. Now if we see the thermal efficiency formula, here we are having 1 minus QR upon QA. If we want to increase the thermal efficiency, we will have to decrease this value, because from 1, if we are subtracting a very small value, then the answer will be greater. But from 1, if we are subtracting a very large value, then the thermal efficiency will decrease. So we have to see that from 1 we have to subtract a small value. Now if QA is constant, then this term QR upon QA will depend only upon QR. So if anyhow I can decrease QR, that is this numerator, if it decreases, then this whole value will be decreased, that is a small value. And from 1, if I am subtracting a very small value, then the thermal efficiency increases. So I'll say that, calling this first of all as equation number 1. So I'll write down, therefore from equation number 1, it is clear that thermal efficiency of a cycle depends only upon heat rejected, as the heat supplied is taken as constant. So for thermal efficiency to increase, that is if you want to increase the thermal efficiency, the heat rejected value should decrease. And how this heat rejected value can decrease, we can see that from the PV and TS diagram, that out of all 3 cycles, here the cycle in red which I have shown here, this is the Otto cycle. Next, the cycle which is in blue, that is diesel cycle, and the cycle which is in black, that is dual cycle. Now of the 3 cycles, if we see, all of them are having the heat rejection at constant volume. So this is the amount of heat rejected from all the cycles. For Otto cycle, the heat is rejected from 4 to 1. For diesel cycle, it is from 4 to 1, and for dual cycle, it is from 5 to 1. The same thing I can show it on TS diagram as well, that the cycle which is in red, that is the Otto cycle, next the cycle which is in blue, this is diesel cycle. At last, the cycle which is in black, that is dual cycle. So now when I am comparing these 3 cycles on the basis of heat rejection, I can see in this diagram that in case of diesel cycle, I'll project this point 4 dash. Onto the temperature. So this will give me a temperature of T4 dash. Then for diesel cycle, in case of dual cycle, the temperature is corresponding to 0.5 at which the heat is rejected. So this gives me temperature T5, and at last for Otto cycle, the temperature at which the heat is rejected is at temperature T4. So for the three cycles, the temperature at which the heat is rejected is different. Now T1 is common because we have assumed that for same compression ratio, so the initial condition is same. So the heat rejected for Otto cycle, here I'll write down. So now here if we see, thermal efficiency will increase if the heat rejection decreases. So here, as I was explaining, the temperature of heat rejection, the temperature at which the heat is rejected, is different for different cycles. For diesel cycle, the temperature at which heat is rejected is T4 dash. For dual cycle, the temperature at which the heat is rejected is T5, and for Otto cycle it is T4. So I'll write down that the heat rejection temperature difference or differences are, first of all I'll write down for Otto cycle. For Otto cycle, the heat rejected QR is equal to, formula is mCV, that is the heat is rejected at constant volume, and the temperature difference, as we see for Otto cycle it is denoted in red, that is T4, and the initial temperature is T1. So the heat rejected is from 4 to 1, as we see here, from 4 to 1 heat is rejected, so it will be T4 minus T1, that is higher temperature minus lower temperature. So this is the heat rejected in case of Otto cycle. Here if the mass is 1, assumed as 1 kg, so it will become CV T4 minus T1, and the unit will be in terms of kilojoule per kg. Next I'll write down for diesel cycle, the heat is rejected at constant volume, so mCV, and the temperature difference for diesel cycle is, it is from T4 dash, as we see T4 dash minus T1. If mass is assumed as 1 kg, so this will become CV T4 dash minus T1 kilojoule per kg. At last for dual cycle, heat rejected Q suffix R is equal to mCV. The temperature difference is, for dual cycle heat is rejected from 5 to 1, so it is T5 minus T1. If mass is assumed as 1 kg, it becomes CV T5 minus T1 in terms of kilojoule per kg. Now, out of all the temperature differences, we can see that T4 dash minus T1 is having the greater value, and this T4 dash minus T1 is for diesel cycle. So we can say that the heat rejected of diesel cycle is greater as compared to Otto and dual cycle. So here I'll write down that heat rejected of diesel cycle is greater. So first I'll write down QR, that is I'm writing it in blue, so this indicates the heat rejected for diesel cycle. Then shortly after that, the heat rejected of dual cycle is greater, that is after T4 dash minus T1, the next temperature difference T5 minus T1 is greater. So after heat rejected of diesel cycle, there is heat rejected of dual cycle denoted in black. So from both of them, the heat rejected in case of diesel cycle is greater than that of dual cycle, and the heat rejected of dual cycle is greater than the heat rejected for Otto cycle, which is from T4 to T1, that is T4 minus T1. So Otto cycle has the least amount of heat rejection. So here Q suffix R in red, that shows Otto cycle, and its heat rejection is less than that of dual cycle. So if we see from this, then the heat rejected in case of diesel cycle is greater, or we can say greatest. Heat rejected in dual cycle is less than diesel cycle but greater than Otto cycle, and Otto cycle has the least amount of heat rejection. So we can say that as the heat rejection of diesel cycle is greatest among all three, that is Otto, diesel and dual cycles, all three cycles. So therefore, as the heat rejection of diesel cycle is greatest, so it means if the heat rejection will increase, then thermal efficiency will decrease. And it is clear from equation number 1 that if we increase this numerator, the whole value will increase, and from 1 the greater value will be subtracted, so thermal efficiency will decrease. So we can say that the heat rejected of diesel cycle is greatest, so this value for diesel cycle will be QR upon QA will be greatest and efficiency will be lowest. So as the heat rejection of diesel cycle is greatest among all three cycles, therefore the thermal efficiency of diesel cycle will be least when compared with the other two cycles, that is when it is compared with the other two cycles, that is Otto and dual. And now we have seen that diesel cycle will have the least efficiency, but if we see out of all the temperature differences, the temperature difference of Otto cycle, that is T4 minus T1, is least. So Otto cycle is having the least amount of heat rejection, so its thermal efficiency will be maximum. It can even be seen with the help of the TS diagram that the temperature difference T4 minus T1 is least, so Otto cycle has the least heat rejection, so its thermal efficiency will be highest. So I'll say that also as the heat rejection of Otto cycle is smallest, like diesel cycle was having greatest heat rejection, so Otto cycle is having smallest heat rejection among all the cycles, all three cycles we have seen here. So therefore the thermal efficiency of Otto cycle will be maximum. So here finally I will say that from the comparison which we have seen, that for same compression ratio and heat supplied, I'll write it again, that for same compression ratio and heat supplied, the efficiency, or we can say the thermal efficiency of Otto cycle will be greater than the thermal efficiency of dual cycle, and the thermal efficiency of dual cycle will be greater than the thermal efficiency of diesel cycle. So here we have compared all three thermal efficiencies based on the same compression ratio and heat supplied, and we have found out that Otto cycle is having the maximum efficiency or thermal efficiency under such conditions, and diesel cycle is having the least efficiency, and dual cycle is in between the efficiencies of Otto and diesel.